A few people have asked and requested videos about applications of the intermediate value theorem and how we write some of these proofs. And so I've got three applications in today's video. The first is sort of a simple application, and this is maybe something you've remember seeing first in a calculus class, and we've done a few examples in our class here as well, and it's just showing that something has a root. So, for example, if we have a function like f of x equals e to the x plus sine of x, we might be asked to show that there's a number c such that when we plug it in, we get 0, right? And so f is a continuous function since it's a sum of an exponential and trig functions. But let's go over into our graphing calculator. So I've got Desmos here, and we can just graph e to the x plus sine of x. We move our graph up a little bit. We can sort of see the behavior of the graph, and that kind of makes sense because when x is negative, then e to the x is really small, so it doesn't really affect the graph. But of course, if x is positive, then that dominates, right? So we can look at this graph and we can say, oh, it actually has lots and lots of zeros. And our idea of the intermediate value theorem is going to be, well, we're going to find one value where it's negative and one value where it's positive. So, I mean, really one input where it's negative and one input where it's positive. And that must mean by continuity, by the intermediate value theorem, that there has to be a 0 somewhere in the middle. So let's see how that works. The values I choose, well, I always choose 0 because either f of 0 is 0, in which case we're done, or else it's going to be positive or negative. So in this case, it was positive. And if I want something that's negative, well, I have to do a bit of work here, but I remember that if I take sine of negative pi over 2, I'm going to get negative 1. And so I'm going to get e to minus pi over 2, and then I'm going to subtract 1. And this is going to be negative. You could argue, for instance, the fact that e to the x is going to be smaller than 1 whenever we have a negative exponent. But in any case, by the intermediate value theorem, there must be some number c in that interval from negative pi over 2 to 0 with f of c equals 0. So the steps that we have here, we've stated that our function is continuous. We found one value where it's positive. We found one value where it's negative. And therefore, we concluded that somewhere in the middle, there has to be some input where we get 0. Okay. So the next application I want to do is similar. It's a little bit more complicated. It's showing that things are equal. So our problem in this case is show there is a solution to cosine x equals x, right? And I want to point out that there's not really any way to solve this, right? I mean, even if you tried taking like the arc cosine of both sides, you would just get x equals, arc cosine of x, right? You still have an x on both sides. You haven't really solved for anything. So this is kind of a tricky problem. And if we try and solve it, well, what we can do is we can graph cosine of x, and we can say, oh, yeah, they definitely intersect. They intersect, looks right there. It looks like they're the point 0.739. Looks to be the answer. I'm sure this is an irrational number. So how are we going to use the intermediate value theorem to do that? Well, the idea is that we have a problem. We have two functions, cosine x and x, and the intermediate value theorem is really a theorem about one function, right? It says if you have two inputs and you know that the range, the output, first output is say negative and one output is negative and one output is positive, then you know that there's got to be something in the middle that's 0. And so we have to reduce this to just one function. And in this case, the way we can do it is just by introducing a new function called g of x, which is just the difference of the two functions, right? And so these two things are going to be equal. Cosine x will equal x precisely when this difference is 0. And so we're really looking for now just zeros of g of x. So now we're in the situation we had before. We have one function we want to show it's 0. And how do we do that? Well, it's continuous. It's a difference of two continuous functions. G of 0, let's just find two values. Well, g of 0, well, let's plug it in. Cosine of 0 is 1, minus 0 is 1. What about g of 100? G of 100 is going to be, well, cosine of 100 minus 100. Well, cosine of anything is going to be between negative 1 and 1. So once we subtract 100, will definitely be negative. And we've got that same conclusion. So because the value at 0 is positive, the value at 100 is negative, there must be some point C in that interval from 0 to 100. Right? So this was like the homework problem in the quiz question where we had to consider the difference of two functions, and then we used the intermediate value theorem with that function. So this would be a good time to maybe pause the video and go back and look at that quiz question. There are solutions to that on the homework solutions, since that quiz had problems from the homework. I do want to point out I used 100 here just because I knew that if I took something and I subtracted 100, I would get something negative. If you had a calculator or some other way of approximating these values, of course you could check here that cosine of 0.7 is going to be bigger than 0.7, and you could plug in different values to sort of get that range in a little bit closer than we did. But our goal was just to show that there was one solution, and that's what we did. Okay. So for our last application is really cool. I found this on Stack Exchange, actually. I was Googling to find cool applications of the intermediate value theorem. And here's what it says. So it says, suppose we know that f is a continuous function and that the value at 0 is the same as the value at 2. That's it. That's all you know. So you just know that the y values at 0 and 2 are the same. And what are we asked to prove? Well, we're asked to prove that there must be two numbers, x and y, in that interval, such that, well, f of x equals f of y, and those numbers are a distance of 1 apart, right? So that's pretty strong, right? It says there must be two numbers, like maybe it's 0.4 and 1.4, or maybe it's 0.055 and 1.055. It says there are two numbers and they've got to be exactly one number apart, but they have to have the same function value. So this is not intuitive at all, right? I was sort of surprised when I saw this, and I wanted to do some examples, and so let's do them. So I've got some examples pre-written on the screen here. So here's one. So it's just a quadratic function. We can check that f of 0 is the same as f of 2. In fact, let's go ahead and just we may as well shift it. Let's make this a -3, right? So f of 0 is -2, f of 2 is -2 as well. And are there 2 points where the y value, where the output is the same? Well, like these 2 points are going to have the same y value, but they're not 1 apart. They're more than 1 apart. But it looks like these two points look like they're about exactly 1 apart, and they have the same y value. So it must be those points that we're looking for. Okay, let's do another one. What about this sign? Let's scroll back up here. So here's 0 and 2. So f of 0 is 0. F of 2 is 2. Yes, and the claim is that there must be two numbers that are exactly 1 apart that have the same output. This number has the same output as this, but they're not 1 apart, right? Because 1 is this whole distance all the way from 0 to 1. And these numbers, I'm worried it might not be true. Oh, there it is, 0 and 1. Right? 0 and 1 are exactly 1 apart, and they have the same y value. So that's interesting. So we got kind of lucky there. Let's do one more. So this is a black function. Here again we have f of 0 is the same as f of 2. In this case, they're both 0. And now we're looking for numbers that are exactly 1 apart, but the same y value. Well, it's not going to be these because these are sort of more than 1 apart. Maybe it's something in here. Yeah, it actually looks like it might be right in here. From this point to this point looks to be about 1, and they have the same y value. Right? So this is pretty cool. I would say that if we did more examples, we might see similar patterns, but it's not clear sort of how to find these numbers. So let's go back to the drawing board. And one idea is to just give these numbers names. So rather than calling them x and y, let's call them c and c plus 1. Right? They're 1 apart, and what we want is f of c equals f of c plus 1. Okay, we just want them to have the same output. And if we look at this, we see it's just like the previous problem. Right? The previous problem, said we wanted f of x minus f of x plus 1 equal to 0, right? So the previous problem we had a difference, and that's exactly what we have here, right? We want to know, well, when can we plug in a number for x and then plug in one more than that and get 0? And so our hint following the previous problem is just to consider the function g of x, which is f of x minus f of x plus 1. Now, you might object to this. You might say, whoa, what's this f of x plus 1? That we're only allowed to subtract functions. This seems like it's something new. There's really nothing weird going on, right? If f is a function, then we can plug in anything to it, right? We could plug in x, and if f was e to the x, then f of x would be e to the x. F of x plus 1 would be e to the x plus 1. So if we do this difference, I just really mean this function here. If f of x equals x squared, then I would mean take x squared and then subtract off x plus 1 squared. Right? So what I've written down really is a function. This thing g of x is a function. And our goal is to prove that g has a 0. Right? So our goal is to show that there's some number so that when we plug in that number we get 0, which would mean, of course, that f of x would be f of x plus 1. G is continuous since f was continuous. G of 0, so let's do our calculations now. So let's figure out what g of 0 is. Well, I guess it's going to be f of 0 minus f of 1. Okay? We don't really know either of those numbers, so let's leave that there. Let's keep going. What about g of 1? Well, g of 1 is going to be f of 1 minus f of 2. Okay? Now, I put an equal sign here, and you may want to pause for a second and see if you can guess what's coming next. What do we know about f of 2? Well, we know that f of 2 is equal to f of 0. So here we have f of 1 minus f of 0. So remember that assumption. If we go way back to our assumption, we had a continuous function, and we know that f of 0 is the same as f of 2. So now where are we? We know that g of 1 is going to be f of 1 minus f of 0. And if we look up just one line, that's the opposite of g of 0. So now, well, let's just think about it. If g of 0 was 0, we're done. Remember, our goal was to prove that g had a 0. Otherwise, well, maybe g of 0 is positive, or maybe it's negative. But then g of 1 will be the opposite, right? It has a negative sign. So g of 0 and g of 1 are going to have opposite signs, and thus by the intermediate value theorem, there's going to be some point c in that range from 0 to 1, such that g of c equals 0. And that was our goal. So this is really cool. We had 3 examples. We started by just showing something was 0. Then we showed that 2 things were equal. And then we sort of did a really cool thing where we had to sort of come up with our own function and solve this slightly more abstract problem. So I hope these have been helpful. In terms of preparing for the exam, please just go and look at the homework questions about the intermediate value theorem. I promise that the intermediate value theorem questions will be very closely related to those. So thanks for watching.